Okay, let's dive into this really fascinating world where the clean, logical power of AI meets the fiery, sometimes chaotic reality of making advanced metals.
So, we've all seen what AI can do, right? It can generate art, it can master complex games. But what happens when you ask it to do something in the real, physical world? Something like forging the perfect alloy. Well, you're about to see how the perfection of the digital world runs smack into the messy, unpredictable nature of physics. And the results? Well, they're not what you might expect.
But before we get into the really tricky stuff, we have to look at where AI has been an absolute runaway success. And that place is the world of steel. For decades, it's been a total game changer. I mean, for the longest time, making a new type of steel was, well, it was more of an art than a science. It was this slow, incredibly expensive process of trial and error, really relying on the gut feelings and experience of seasoned metallurgists. Then AI showed up. And just look at the difference. It's just staggering. We're talking about taking a process that used to eat up 18 months and $500,000 and shrinking it down to a few weeks of computer time. AI can run millions of virtual experiments, tweaking recipes and temperatures in ways that would be physically impossible to do in a lab. This is really where AI just excels. It takes all that guesswork and throws it out the window. That whole black box of metallurgy, where you mix things together and just hope for the best, it suddenly becomes this transparent, highly optimized process. You know exactly what you're going to get before you even turn on the furnace. Okay, so that's steel. Sounds like a solved problem, right? Well, here's where our story takes a sharp turn. Because the moment we step away from steel and into the world of non-ferrous alloys, we're talking aluminum, titanium, nickel, the stuff used in jet engines and high-performance bearings, that perfect digital playbook, it suddenly falls apart. And here's the fundamental reason why. With steel, the main ingredients are the stars of the show. They dictate how it behaves. But with these advanced non-ferrous alloys, it's the tiny, almost invisible details that can cause catastrophic problems. I'm talking about a few stray atoms of oxygen or a trace impurity, completely changing the properties of the final material. This quote here, from an analysis of a failed gearbox, just perfectly illustrates how predictable steel is. The engineers know exactly what treatment was applied to each specific gear. It's a well-defined, almost routine process. That kind of certainty, well, it's a luxury you often don't have with these more advanced, more sensitive alloys. So why did the AI models stumble? Well, the best analogy is that the AI is using a digital cookbook. But this cookbook has no idea about the humidity in the kitchen or if a tiny speck of dust falls into the flour. The databases the AI learns from are pristine. They just don't capture the messy, microscopic chaos of the real world. For example, let's talk about atmosphere sensitivity. The very air inside the furnace can be your enemy. A tiny bit of moisture, a small oxygen leak you can't even detect, it can completely alter the final product in ways the database just doesn't know about. It's a huge problem. And then you have these things called compositional inhomogeneities. It's a mouthful, but think about it like trying to mix sugar into your coffee. If you don't stir it perfectly, you get those clumps at the bottom, right? The same exact thing happens in these alloys, but on a microscopic scale. And those tiny, unmixed clumps, they become weak spots. They're where cracks start. Now, this one is really mind-bending. During heat treatment, tiny, temporary structures, we call them metastable precipitates, can pop into existence and then vanish in fractions of a second. They are absolutely essential for an alloy's final strength, but trying to measure them is like trying to photograph a lightning strike with a slow shutter camera. Our conventional tools are just too slow to see them happen. So what do you do when you're fighting an enemy you can't even see? You build better eyes. And that is precisely what scientists have been doing, developing a whole new toolkit to actually peer into the heart of these materials and see what's really going on in real time. And we're not talking about small upgrades here. These tools are incredible. We're talking about electron microscopes, so powerful you can literally watch individual atoms move around. Or using a synchrotron, a massive particle accelerator, to generate X-rays that can map out those tiny, dangerous clumps we talked about. This is the tech we need to really get what's going on. This represents a fundamental shift in our whole approach. We're going from analyzing the crime scene after the fact, looking at a cold piece of metal and guessing what happened, to watching the event unfold live, at the atomic scale. And this generates a completely new kind of data.
rich, physically grounded data that an AI can actually learn from. So you see, it was never that the AI was dumb, it's that we were feeding it bad or at least incomplete information. It's like trying to learn a new language with a dictionary that's missing half the words. Now, finally, we can give the AI the smart data it needs to truly understand the physics of what's happening. And what this creates is this amazing, powerful feedback loop. Better experiments generate smarter data. That smarter data trains a better AI. And that smarter AI helps us design even better experiments and augment the knowledge of human experts. It's this virtuous cycle of improvement. And I want to be clear, this is not some pie-in-the-sky idea for the future. This is what's happening right now. At major global conferences, this is the main conversation. How do we integrate these incredible new experiments with intelligent systems to build the next generation of tools for designing materials? So what we're really seeing is the bridge being built between the clean, digital world of AI and the messy, physical reality of materials. And when that happens, it opens the door to a whole new age of discovery. It really makes you wonder, doesn't it? What materials that we once thought were impossible are now finally within our reach?